So this video is going to start our discussion of acid-base titrations. The way I've decided to organize this video is, in this video I sort of go through all the concepts, but I don't do any of the actual calculations. And so then there are separate videos for the different types of calculations that we can do. And so the way you can watch this, I would suggest two ways, and doing whichever way appeals most to you. One would be to sort of watch this all the way through and sort of get the broad overview of the topic, and then go back and look at the individual videos on the calculations. Or what you might want to do is watch this video and then pause it at different points and watch the calculations associated with what we're talking about in this video. And what I'll try to do is, when there are calculations related to what I'm talking about, I'll let you know that, so that if you want to follow that second approach where you stop this video and go and watch the calculation videos, you can do that. So there are lots of different types of titrations. The most common, and the ones that we're going to be talking about here, are acid-base titrations. But in general, titration is a controlled addition of a volume of a known concentration, and that's what's in the burette, and then we have an unknown solution or an unknown concentration in this case, the beaker, or in the titrations that we've done in class, we've often used an Erlenmeyer flask. But the key feature of a titration is the equivalence point. And when we do acid-base titrations, typically what we monitor over the course of the titration is we keep track of the volume of what we call the titrant. That's what's in the burette. That's the thing that has a known concentration. And so in this example, there is sodium hydroxide in the burette, and then we have some acid in the beaker, or we could use an Erlenmeyer flask. And so initially the pH is very low because it just contains an acid. And then as we add sodium hydroxide, the pH increases, and it increases gradually at first. And then when we get to this point called the equivalence point, the pH changes very rapidly before slowing down again as it continues to increase. And so this equivalence point is one of the key features of any titration. And it is at the equivalence point where the moles of acid that I started with is equal to the moles of base that I've added. So this is definitely an important thing to sort of write down and star. This is one of the most important features of a titration. At the equivalence point, the moles of acid that we started with is equal to the moles of base that we added. It doesn't matter whether we're doing a titration of an acid with a base or a base with an acid. This will always hold true. Now, I just wanted to make a callback to one of the previous videos from the previous lesson plan. And all of the calculations involved in the different types of titrations that we might consider are just examples of the acid-base reaction calculations that we practiced before, right? These were the two-step calculations, where we first did a stoichiometry calculation, where the reaction is going to completion. This is where we used a BCA table, and because we're doing stoichiometry, we had to work in moles. And then that's followed up by looking at what's present in the after the reaction row to decide what to do next. Right? So if we have any strong acid or strong base present, then we just ignore everything else and use this to determine the pH. Right? We'll have the moles in the BCA table, divide that by the volume to get the concentration. If we have the concentration of either H3O plus or OH minus, the strong acid or the strong base, then we can determine the pH from that. If there is only a weak acid or only a weak base present, then we know how to do this. This is just calculating the pH of a weak acid or a weak base, and this is just an ice table problem. If I have both a weak acid and its conjugate base, or vice versa, the conjugate base, or the base and its conjugate acid, then we have a buffer, and so we can just use the Henderson-Hasselbalch equation. So we first do the stoichiometry, and then we do the follow-up, potentially equilibrium calculation. But of course, if there's any strong base, meaning OH minus, or any strong acid, meaning H3O plus, then we don't need to do the equilibrium calculation. We just use the OH minus or the H3O plus to find the pH. Okay, so let's first consider a titration of a strong acid with a strong base. And so this is typical of what the titration curve would look like. And again, when we're around the equivalence point, the pH changes very rapidly. An important thing that I would probably make a note of is when we have a titration involving a strong acid and a strong base, the pH at the equivalence point is always 7, because at the equivalence point, the moles of strong acid that we started with is going to be equal to the moles of strong base that we added. At the equivalence point, there isn't any excess. Those two values are equal, so they'll completely neutralize each other, and so the pH is going to be 7. Now, we can do calculations for what the pH should be at different points in the titration, and so let's consider them. So before the titrant is added, that means we only have the strong acid that we started with. And so calculating the pH is just calculating the pH of a strong acid. If we're before the equivalence point, we have to do the stoichiometry step, but if we haven't reached the equivalence point yet, the base is going to be the limiting reagent. And so I'm going to have leftover H3O+. And so once I finish the stoichiometry and see how much H3O+ is left, I can use that to find the pH. We've already talked about what the pH should be at the equivalence point. It should be 7. And then after the equivalence point, now we'll have added excess base, right? So we've added more base than we needed to get to the equivalence point. And so you're going to still do a stoichiometry step, but at that point, we're going to have leftover hydroxide, and so we'll use that hydroxide to determine the pH. All right, so if you want to look at the calculations related to strong acid, strong base titrations, this is a good time to pause this video and go watch, I think I have 2 videos on calculations related to this. Okay, so moving on, I'm not going to do any examples of it because it's basically the same, but if we have a titration of a strong base, which is in our flask, and then we have the strong acid in our burette, the titration curve is just going to be the mirror image of the previous titration that we considered, right? The pH starts out high when we have only base present. As we add acid, the pH gradually decreases until we get close to the equivalence point where the pH changes rapidly. The pH is again equal to 7 at the equivalence point, and as we go past the equivalence point, now the excess H3O plus is used to determine the pH. Okay, now let's consider the titration of a weak acid by a strong base. So there are a number of differences, but as we've been talking about, these are still these 2-step type problems. We first have a stoichiometry problem, we then have an equilibrium problem. And again, there are 4 regions that we're basically interested in with the titration of a weak acid by a strong base. So before any base is added, all we have is weak acid in the flask. And so we know how to calculate the pH of a weak acid, assuming we have the Ka. When we're before the equivalence point, but after we've started adding base, now we have a buffer, right? So when we add the strong base, that's going to convert some of the weak acid into its conjugate base, but I haven't used up all the acid because I haven't gotten to the equivalence point yet. So before the equivalence point, you're going to find, after you do the stoichiometry problem, that you have the weak acid you started with and some of its conjugate base present. So you effectively have a buffer, and so the easiest way to calculate the pH then is using the Henderson-Hasselbalch equation. Now when we're at the equivalence point, for this type of titration, the pH is not equal to 7, because at the equivalence point, all of the weak acid will have been converted into its conjugate base. And at the end of the stoichiometry problem, all of the weak acid and all of the hydroxide are going to be gone, and all you have is a weak base. So we know how to do those calculations, right? It's just calculate the pH of a weak base, but the pH will always be above 7, because you don't have a neutral solution at that point. You have only a weak base. And then as we move after the equivalence point, now we're going to have excess hydroxide. And so the problem here is just after the stoichiometry problem, you'll have leftover OH minus. And so you can use that to find the pH. Alright, so this is another good place to pause the video. I have separate videos on each one of these regions in a titration and how to calculate the pH in that region. But remember, these are all just acid-base problems, where you first do a stoichiometry problem, and then decide what you have left and do the appropriate equilibrium problem, if indeed you need to do that. If you have H3O plus or OH minus left over, then you would just use those to determine the pH. Now, I do want to talk about a very important point in the titration of a weak acid with a strong base, and that's called the half-equivalence point. As an example, let's say, we don't have any numbers on this graph, but let's say the equivalence point occurred at 50 milliliters. Then the half-equivalence point would occur at 25 milliliters. Now, what's important about the half-equivalence point is the fact that we've added exactly half the hydroxide we need to neutralize the acid. That means exactly half of our starting acid will have been converted into its conjugate base. And so, at the equivalence point, the amount of acid that we started with is equal to the OH concentration, but at the half-equivalence point, the concentration of our starting acid is equal to the concentration of its conjugate base. And so we have a buffer at this point, like we do at any region, or at any point before the equivalence point. So we can use the Henderson-Hasselbalch equation to find the pH. But if HA and A minus are equal, then this ratio will be 1. The log of 1 is 0. So at the half equivalence point, the pH is equal to the pKa. And so that can be very useful to us. This is true for any titration of a weak acid with any strong base. And so if we have an unknown acid, this can be very useful because this can allow us to determine the Ka. We can just do the titration, right? Find the equivalence point, then locate the half equivalence point, read the pH at that point on the titration curve. That will tell us the pKa, so we can determine the Ka, and this could be used to determine an unknown acid. We could compare the Ka of our unknown acid with other common Kas of known acids, and thereby determine what our unknown is. So the half equivalence point, a very important part of a titration curve, and an important thing to remember. So let's look at some similarities and differences between strong acid and weak acid titration curves. One thing to note, if the concentration of two acids, say our strong acid and our weak acid, are the same, if we titrate that with the same concentration of base, the equivalence point will happen at the same volume, right? Because the equivalence point just determines the volume needed for the moles of acid that we started with to be equal to the moles of base that we added. Doesn't matter whether it's a strong acid or a weak acid. It's just that the moles are equal between the acid and the base, and so the equivalence point will always happen at the same volume. Now, a difference in the equivalence points is our strong acid, its equivalence point is going to be, the pH is going to be 7. For our weak acid, the pH is going to be higher than 7. Now, in terms of the pH before the equivalence point, assuming the two acids have the same concentration, the weak acid will always have a higher pH, right? Because the strong acid completely dissociates, it's going to have a lower pH than essentially the buffering region of a weak acid titration curve. And the importance of the half equivalence point in the weak acid isn't really relevant in the strong acid. We're essentially assuming that the Ka for a strong acid is infinite, that the acid is completely dissociating. So there is no special significance of the half equivalence point in the case of a strong acid being titrated by a base. So this slide is really just reinforcing a lot of the things we talked about on the last slide. What we're seeing in this figure is the titration curves for a number of different weak acids with the same concentration of sodium hydroxide. And notice since all of the acids we're saying have the same concentration, the equivalence point happens at the same volume. But of course, the pH at the equivalence point is going to vary for the different acids. You can also see at the half equivalence point for these different acids, right, the pH of the half equivalence point will also be higher for the weaker acids. The weaker the acid, the smaller the Ka and the larger the pKa, and so the pHs are shifted to higher values for the weaker acids. Right, now, in most of the examples we do in this class, we're often titrating acids with bases, but there's no reason why we can't do the opposite. And so we could certainly do the titration of a weak base with a strong acid. But this is very similar to the titration of a weak acid with a strong base. Again, we have 4 regions that we're interested in. Before we add any acid, all we have is weak base, so we're just calculating the pH of a weak base. After we've added the acid, but before the equivalence point, we're going to convert some of the weak base into its conjugate acid. And so we have another buffer problem. At the equivalence point, for a weak acid being titrated by a strong base, the pH is determined by the hydrolysis of the base that's left over. In this type of titration, a weak base being titrated by a strong acid, the pH is determined by the weak acid that is the only thing present at the equivalence point. And then as we move past the equivalence point, we're adding excess strong acid. And so after we do the stoichiometry problem, however much H3O plus is left over, that's how we determine the pH. All right, if we look at the titration curve of a weak acid being titrated with a strong base, it basically just looks like a flipped over weak acid strong base titration. In this case, for a strong acid, strong base, the pH is 7. For a weak acid being titrated by a strong base, the pH is above 7. For a weak base being titrated with a strong acid, the equivalence point is less than 7. The half equivalence point is still relevant. At the half equivalence point, the pH is still equal to the pKa of the conjugate acid. We can also think about it as the pOH is equal to the pKb of the weak base. Although, if we're going to use the Henderson-Hasselbalch equation, I think this relationship is probably maybe the one that's more useful. Okay, and I wanted to just end this slide on a discussion of polyprotic acids. So we're not going to do too much with polyprotic acids, but if I gave you a titration curve, I think you should be able to tell me whether it's a monoprotic acid, a diprotic acid, a triprotic acid, etc. For polyprotic acids, we essentially have what looks like multiple titration curves being stitched together. And so we have, in fact, 3, this is an example of a triprotic acid, so we have 3 equivalence points. If we look for the regions where the pH is changing rapidly, each one of these represents the equivalence point for taking another one of the protons off of the polyprotic acid.